Have you ever just stopped and wondered what actually makes the wind blow? It feels like this invisible, totally mysterious force, but really, it's all driven by some surprisingly simple physics. So today, we're going to pull back the curtain on the atmosphere and find out exactly what gets the air moving.
Okay, I want you to picture a perfect day at the beach. You feel that nice, cool, refreshing breeze coming in off the water, right? Well, believe it or not, that simple experience holds the key to understanding, well, everything, from a tiny little gust of wind to the massive wind patterns that circle the entire globe. That sea breeze, that's our starting point.
If you remember just one single thing from this whole explainer, please make it this. This is the golden rule of wind. It's so simple. Just like water flows downhill, air always flows from areas where it's kind of piled up, that's high pressure, to areas where there's less of it, low pressure. Every single wind on this planet, big or small, follows this one fundamental rule.
So there's a fancy science name for this movement, of course. It's called the pressure gradient force. Now, I know that sounds a little complicated, but it's not. It's just a way of saying that when you have a difference in pressure over a certain distance, a gradient, it creates a force. And that force, well, that's what we feel as wind. Simple as that.
Right, so if pressure is totally invisible, how in the world do we actually see where it's high or where it's low? Well, meteorologists have this amazing tool for that, the weather map. And we're about to learn how to read these maps so you can see these invisible forces at play for yourself.
You see all those squiggly lines on a weather map? They're called isobars. The name is a clue. Iso means equal and bar means pressure. So an isobar is just a line connecting all the places that have the exact same air pressure. A good way to think of them is like contour lines on a hiking map, but instead of showing elevation, they show pressure.
And this right here is the perfect way to picture it. Seriously, just imagine the high-pressure areas are the top of a hill and the low-pressure areas are the bottom. The pressure gradient then is just how steep that hill is. A ball is obviously going to roll down the hill, and the steeper it is, the faster it goes. Air does the exact same thing.
So here's how you can use this. When you look at those isobars on a map, pay attention to the spacing. If the lines are really far apart, that's like a very gentle slope, a weak pressure gradient, and that means you're only going to get light winds. But when you see those lines packed tightly together, wow, that's a super steep pressure hill, a strong pressure gradient, which means you are going to get some strong winds.
Okay, let's put all this theory into practice. We're going to head back to our day at the beach and trace the step-by-step story of how that classic sea breeze gets created, using everything we've just learned about pressure and those imaginary hills.
All right, let's walk through this. First up, step 1. Before the sun's even up, everything's pretty much in balance. The land and the sea are about the same temperature, so the air pressure is stable. No pressure hill, no wind. Then, in step 2, the sun rises. The land heats up way faster than the water does. So the air right over the land gets warm, it expands, and it starts to rise. That leaves behind an area of lower pressure, right at the surface. And finally, step 3, where the magic happens. That rising warm air flows out over the cooler sea, where it cools down, gets denser, and sinks. All that sinking air piles up, creating higher pressure at the sea surface. And there you have it. We've created our pressure difference. High pressure over the sea, low pressure over the land. The wind has to flow from high to low, and boom, you get that classic refreshing sea breeze.
Now, get ready for this because this is where things get really, really cool. That small-scale circulation we just watched happen at the beach, the exact same principle is responsible for the massive wind patterns that wrap around our entire planet. We're just scaling the whole idea way, way up.
And here's the big aha moment. It all comes down to one thing: unequal heating. Just like the sun heats the land faster than the sea, it also heats the Earth's equator a whole lot more than it heats the poles. That fundamental imbalance, that is the engine that drives all of our planet's winds.
I mean, this chart says it all, right? The equator gets blasted with direct, intense sunlight all year round. This creates this massive zone of warm, rising air, which means a permanent low-pressure belt. Meanwhile, the poles get weak, indirect sunlight, making them incredibly cold. This creates dense, sinking air and permanent high-pressure zones. The atmosphere is just constantly trying to balance this huge temperature and pressure difference, and that whole process is what creates our global winds.
So, let's bring this all back to something you see pretty much every day, the weather forecast. How does all this connect to what the person on the news is pointing at on that big map?
You know those big blue H's and red L's on the weather map? Well, they aren't just random letters. They represent huge domes of high pressure and troughs of low pressure moving across the globe. They are just the really, really big versions of the pressure differences we saw at the beach.
And now you know exactly what they mean. A high-pressure system, that big H, is an area of sinking, stable air. That's why it usually brings clear skies and calm weather. A low-pressure system, the L, is an area of rising, unstable air, which is why it's almost always connected to clouds, storms, and all kinds of active weather.
And there it is. When you boil it all down, that's it. Whether we're talking about a gentle sea breeze or a jet stream that spans a continent, wind is nothing more than the atmosphere's constant, tireless effort to correct imbalances. It's a planetary balancing act, always moving energy from where there's too much to where there's not enough.
So I'll just leave you with this final thought to chew on. If all wind is just the atmosphere trying to find its balance, what does something as incredibly powerful and destructive as a hurricane tell us? Well, it must mean there's a truly massive imbalance that the atmosphere is trying to fix, and it's doing it in the most extreme way possible.